In this work, we present TrackDLO, a method for tracking the shape of deformable linear objects under occlusion. Deformable linear object shape tracking takes RGB-D stream as input, then extracts a set of nodes and edges to represent the shape of the object. One of the approaches for solving this problem is non-rigid registration. Here we list out the existing deformable linear object shape tracking works that are most similar to ours. These include coherent point drift plus physics, structured preserved registration, constrained deformable coherent point drift, and constrained deformable coherent point drift 2. All these methods are based on the two non-rigid point set registration methods listed on top, coherent point drift and global local topology preservation. Our proposed method, TrackDLO, accurately tracks the shape of deformable linear objects in real time under occlusion without information from modeling, simulation, visual markers, or contact. This is achieved through preserving the total length of the deformable linear object, as well as imputing the displacement of occluded nodes from that of the visible nodes using Motion Coherence Theory. TrackDLO tracks self-occluding deformable linear objects without modeling entanglement. This is achieved by replacing the Euclidean distance with the geodesic distance in the kernel, describing how pairs of nodes influence each other's motion, as well as in the registration associating DLO nodes to the points in the 3D point cloud. TrackDLO introduces a kernel that only penalizes lower-order spatial velocity derivatives, which leads to improved accuracy for tracking under occlusion. We performed quantitative evaluations for different kernels, and then selected the one with the lowest error overall. We also released our code and data publicly on GitHub. The TrackDLO algorithm takes two things as inputs, the point cloud at the current time step t and the DLO nodes at the previous time step t-1. First, TrackDLO estimates the visibility of DLO nodes and registers the visible nodes to the current point cloud. Then, it remaps the visible node positions to preserve the distance between adjacent nodes. Finally, it registers all DLO nodes to the new point cloud. The visible nodes will have the remapped node positions as references, while the occluded nodes will have their displacements imputed from the displacements of the visible nodes. Geodesic proximity is encoded in the imputation step.
Tracking performance is quantified using the center points of blobs obtained through color thresholding on a marked rope as ground truth node positions. The per node error is the average distance between nodes in the tracking result and the closest point along a piecewise linear curve defined by the ground truth node positions. The evaluation frame error mirrors the per node error to guarantee symmetry. Two motion scenarios, referred to as perpendicular motion and parallel motion, are used to quantitatively evaluate tracking performance. Synthetic occlusion is injected during tracking by masking a region of the DLO segmentation. The perpendicular motion scenario compares performance under occlusion of the midsection of the DLO, and the parallel motion scenario compares performance under occlusion of one of the tips of the DLO. TrackDLO is compared to three other methods of DLO tracking, including CDCPD2 with and without gripper motion information, CDCPD, and GLTP. In the perpendicular motion scenario, the shape of the DLO estimated with TrackDLO best aligns with the ground truth shape on the final frame of the tracking sequence, while the shapes estimated with other algorithms significantly deviate from the ground truth under midsection occlusion. In the parallel motion scenario, only two methods can track an occluded tip of the DLO as it moves through occlusion. In the other three methods, the tracking shape is compressed to align with only the visible portion of the object. The high accuracy of the TrackDLO algorithm in these two scenarios is evident in its low frame error, shown on the right. A stationary scenario is also used to quantitatively evaluate tracking performance under varying occlusion sizes, testing tracking stability. The size of the synthetic occlusion block is varied as a percentage of the total number of nodes of the object, and the DLO remains stationary throughout the tracking sequence. TrackDLO estimates the shape of the DLO with the lowest final frame error in this scenario as well.
We also performed 9 experiments to qualitatively evaluate the performance of our algorithm and 3 other existing algorithms. These experiments highlight cases in which our algorithm succeeds and other algorithms fail, in which our algorithm fails while other algorithms succeed, and in which all algorithms fail. Due to time constraints, we will only show 3 of the experiments. All experiments can be found in our supplementary video. We used 2 objects made of different materials for the experiments, a 3 feet long rope and a 3 feet long rubber tubing. Note that the zip tie and tape on these objects are simply for preventing them from falling apart. They are not designed to enhance tracking performance and are not input features to any of the tracking algorithms. In experiment 1, we test the preservation of object topology for knot tying. TrackDLO successfully tracks the object's complex topological shape, while the other algorithms fail to resolve self-crossing. In experiment 2, we test the accuracy of tracking under external contact. Note that the pose and shape of the obstacle are inputs to the CDCPD2 algorithm, but not to any other algorithms. In experiment 3, we test the accuracy of tracking under large-scale self-occlusion. TrackDLO accurately tracks the shape of the object when it is coiled, while the other algorithms fail to track the shape under large-scale self-occlusion.
In conclusion, TrackDLO is a real-time, vision-only algorithm for DLO tracking. It is robust under tip, midsection, and large-scale self-occlusion. TrackDLO achieves the lowest tracking error compared to 3 other methods of DLO tracking. We thank the Illinois Space Grant Consortium, NASA, and the Sofin Memorial Fund for supporting this work. Please find the TrackDLO code and data on GitHub using this QR code.